So we're going to go through a simulation here to understand what forms a sampling distribution of proportions. So we're going to set it up as rolling a fair die 60 times, and we want the proportion of ones that show up. So it's going to come through with that as based on how a die is built. So we should have this 1/6 coming through. The proportion, if you roll it 60 times, 1/6 of the time, you should be getting out 1. Something we're going to use within the program is that 1/6. So if this is our population proportion, is 1/6. That's going to be the same thing as a 0.1667. So it's the idea if we roll the die, no matter how many times, 16.67% of the time, you should be getting a 1 coming out of there. So we're going to use a simulation. This simulation is from a book created by Locke, and they have this program called StatKey that we use. This program StatKey will run our simulation with making the sampling distribution of proportions. So some things that I had to set up for us is the idea of rolling a die 60 times. So that's where I set my sample size to 60 here. So I added that to be 60. And then the proportion, I wanted to make sure the proportion was that 0.1667 to represent that 16.67% of the time rolling a 1. So we're going to have these 3 windows working together here to make this sampling dot plot of our proportions. So let's start with talking about the original population. So you can see it says proportion 0.1667. So what we're having here is there's always going to be some population proportion that's telling us how all samples should behave and the percentage of times we expect success. So original population is just going to be this idea of a population proportion. So some value for P. So you have a population proportion. Let's see what happens when we take one sample. So we take one sample. This sample window right here, you can see is we have our sample size of 60, and the count here that's using that proportion of 1/6 is saying randomly how many times a 1 popped up, given that it had a 1/6 chance. So we saw 1 pop up 12 times out of the 60 rolls, which gives us this proportion of 0.2. So again, these are random samples, so while we would be expecting to get this 0.1667 most of the time, we should be close by. There's going to be some variability. We might get some weird samples, but it should work that most of the time we're close to this, and then it's more unlikely as we get further away, which is describing our bell-shaped curve, which is exactly what we want here. Again, a bell-shaped curve lets us calculate probabilities, find cutoff points. All we have to do is understand how it's centered and the standard deviation. So this one sample was taken, counted how many times we had a success out of our whole sample, and then it got this proportion here. And this right here is a sample proportion. So that's what the second window is showing us. It's a generated sample proportion, which those sample proportions, that is our P hat. And then we do have a specific sample size here. So from our sample size of 60. So we'll talk about how sample size changes things. What happens when you take a small sample size versus a large sample size like this. So from there, the third window, the big one here, is our sampling distribution, or how it should behave if we did this infinitely many times. And what happened is once you took that sample and got that sample proportion, that's the dot that was plotted right there at 0.2. So this collected a P hat value. And if we generate another sample, so in this case, actually we saw it exactly 1/6 of the time, so that's a rare case where we land exactly on the population proportion, or not rare, that's where we expect to land. And that plotted the point there at 0.167. So we have these 2 P hat values from 2 random samples that were taken based on this population proportion with a sample size of 60. And what we want to do is see how do these P hat values behave if we keep running the simulation. what happens if we get close to this idea of infinitely many times? So there's this nice generate 1,000 samples, and that's going to run that 1,000 times. And even you could click it again for good measure, 'cause the more samples, the better. And what we end up with here is this sampling distribution of proportions. So that's our third window. It's a collection of sample proportions, meaning it's a collection of those p-hat values from samples of size 60. So that's how these windows are working together. We have the set population proportion. We're generating samples based on how things should be behaving with a sample size of 60 and a given population proportion, but we get some variability in there, and we're collecting those sample proportions to see how do they distribute, so we can see the behavior of those sample proportions. So let's talk about the behavior. What's the mean doing, and then what's the shape? So this shape is pretty much bell-shaped. Yeah, we could argue there might be kind of a tail there, but really, if we kept doing this, it should even out to a nice bell-shaped curve here, with us expecting to land close to 0.167, a little variability below, a little variability above. So, in terms of the mean on our window here for the sampling distribution of proportions, that's describing the average of these values, or the average of our p-hat values. And the symbol that we use for this is, it's a population mean, because if we run this infinitely many times, we'd have all of the data, and we're averaging them, and then we want this little subscript of p-hat, since it's an average of those sample proportions. So we have this average of sample proportions. So that's what the mean refers to. And as we saw, this should be exactly equal to our population data, our population proportions specifically. Should be equal to that population proportion. So that's the value we should be getting out most often as it averages out. The shape of the distribution, once we clicked on that button and clicked on it a few times, is normally distributed, which is exactly what we want. We want that nice bell-shaped curve. And what we're going to go into is sample size again, and the benefits of having a large sample size. So it's normally distributed when we have that sample size of 60 in this case, but let's see what happens when we take a small sample size versus a large sample size. So we're going to set the sample size to 10 and compare that to what happens when we have a sample size of 100 and see, do we have a bell-shaped curve both of the times? So if I change my sample size to 10, which is the idea of just rolling the die 10 times and having that 1/6 chance of seeing a 1 coming up, I'm just going to generate a bunch of samples. Meaning I'm rolling the die 10 times and counting how many times I see a 1. So what we see here is something that's clearly right skewed. And it's because when we have smaller sample sizes, it's that more weird things can happen. Basically, we can get stranger results if we're only repeating the process 10 times. It's not enough to clearly see what's going to be the trend. So with that small sample size, we end up with skewed data. Whereas if I bump this up to 100 and generate that sample 100 times, nice bell-shaped curve here, and centered at where we expect to be centered. So we're going to be seeing there's a sample size condition here of making sure we have a large enough sample size to have a normally distributed graph. So this was skewed, which again, we don't want skewed data because we can't calculate the probabilities with that. But with a large sample size, that was normally distributed, which is exactly what we want. So on the next page, we'll talk about what the actual sample size condition is to make sure that it's going to be normally distributed. So as we take larger sample sizes, the sample proportions should be behaving more as we expect them to. When we take these larger sample sizes, we're expecting those p hat values to be closer and closer to 1/6 almost all of the time. So the p hat values are closer to the population proportion. And this is that law of large numbers that we talk about back in probability, where the more you repeat a process, the more that sample value is going to behave how we expect. Like flipping a coin, if you only flip a coin 5 times, you might not get that exact 50% of heads, but if you flip a coin 1,000 times, it's going to even out to be very close, if not exactly equal to that population value of 0.5. So if we're taking larger sample sizes and these sample proportions are closer and closer to p, then our standard deviation of this bell-shaped curve is going to be smaller and smaller, these larger sample sizes. Because as we take larger sample sizes, there's less variability in our outcomes if they're all behaving very close to our population proportions. So it decreases with large sample sizes. So standard deviation and sample size kind of behave in an opposite way. If you have a large sample size, you're going to have a small standard deviation because larger sample sizes average out, and that's where we lose those extreme values. They don't have as much influence. Whereas if we take small sample sizes are going to lead to a large standard deviation. That's because with small sample sizes, it's not evening out. It's too many extreme values can come through, and that grows our standard deviation. So simulations to show how the proportions behave, how we need a large sample size in order to get this bell-shaped curve. Then once we have this bell-shaped curve, once we understand the center of it and the standard deviation, we can go and start calculating probabilities.